Hello everyone, and I hope you enjoyed my last video on working out the centre of mass of a lamina. The question was taken from a past paper question. We were given a lamina that consisted of a right angled triangle. Sitting on top was a semicircle, and it was all put on a well-defined coordinate system. And we were asked to find the centre of mass of the whole, and we did that. Now, what I'm going to do in this video is show you a different method for working out the centre of mass of the triangle. Now, in the previous method, all we had to do was use the average of the coordinates, and we got an answer of 2, 6, and that was the proper and appropriate thing to do for that particular shape and for this particular question. But suppose we have a different shape that's not defined by points. Suppose we've got a shape defined by the curve f of x is equal to x squared, or f of x is equal to x cubed, or f of x is equal to the square root of x. And all those curves, say, are bounded by the x-axis. And we were asked to find the centre of mass of those shapes between two limits. How would we go about doing that? Well, we can't use the centre of mass. We can't use the average of the coordinates. That's for certain. We have to use a different method. Now, I'm going to show you that different method when it comes to working out the centre of mass of the triangle from the previous question that we know has got a centre of mass of 2, 6. If we use this more complex process to work out the centre of mass of our triangle, it's only a short step away from working out the centre of mass of much more complex shapes defined by more complex functions. Now, before we look at a continuous distribution of mass, let's look at how we first defined the centre of mass for discrete masses. And let's suppose we've got the x-axis here, and suppose we've got a number of bodies on the x-axis of well-defined mass and well-defined coordinates. And we're asked to find the centre of mass of the whole. Well, there's a formula there. You can see it for yourself. m1x1 plus m2x2 divided by the total mass. Now, this is a purely mathematical problem at this instance. It's got great physics utility, but we're thinking just now purely of the mathematics. Now, the products mx are called moments, and they're moments about the y-axis, because remember, if we've got m1 x1, x1 is the distance from the y-axis. x2 is the distance from the y-axis. This is why they're called moments about the y-axis. So the total moment about the y-axis is the sum of the top line. Divide that by the mass, you get the centre of mass on the x-axis. If you multiply the centre of mass by the total mass, you get the sum of the moments. And that's a useful way of seeing it, because it allows us to think of the centre of mass as a position where all the mass can be concentrated to give you the exact same moment. Now, and it's the exact same argument for the y-axis. In this case, the product m1y1 is the moment about the x-axis. So now we have formulas for the centre of mass for discrete masses along the x-axis and along the y-axis. How do we find the centre of mass for a lamina, which is a continuous distribution of mass? How do we do that? Well, leading up to that analysis, I'm going to show you a particular problem using discrete masses. Then we'll lead up to that. The problem we've got here, well, is this. We've got 4 2-kilogram masses, all at x equals 4, and going along the y-axis in units of 1, 0, 1, 2, 3. And we're asked to find the centre of mass of that arrangement. The details are shown for you, but the answer is interesting. The centre of mass of that arrangement is x is equal to 4 and y is equal to 1.5. X is equal to 4 is obvious, because all the masses are at the x equals 4 coordinate. But when it comes to the centre of mass for the y coordinate, well, that's not 0, that's not 1, that's not 2, and that's not 3. No, it's exactly half of 3, 1.5, half of the maximum value. And this is the centre of mass of that symmetrical column of masses. Bear that in mind when we do the next part. So how do we find the centre of mass of a lamina? Well, let's look at a general shape then. Here we have a lamina bounded by the curve y is equal to f of x and the x-axis from A to B, and it's got an uniform area density sigma, which is simply the mass per unit area. How do we find the centre of mass of that shape? Well, let's start off with a definition for the x-coordinate of the centre of mass. And that's defined as this. X of the centre of mass is equal to 1 over the total mass into the integral from A to B x dm. And that's how it's defined. And that gets you your answer. What does it mean though? Well, x represents an x-coordinate and dm represents a tiny wee mass at that x-coordinate. So what we have to do in this particular case is if we divided our lamina into an infinite number of masses of dm, multiply those masses by their x-coordinate, then we have an infinite number of moments about the y-axis, and that's fine. Then we add them all up, as indicated by the integral sign. Remember, the integral sign indicates is saying you're adding an infinite number of entities, in this case x dm's. Add them all up, divide by total mass, and lo and behold, you have your centre of mass for the x-coordinate of the lamina. And isn't that great? And that's basically what we have to do. But the problem is this though. It's impractical to divide a shape into an infinite number of smaller shapes and then add them all up, multiplying by the coordinate. That's impractical. So we need to find a way around it. So how do we proceed from here then? Well, we can't add up an infinite number of moments, but we do have a process called integration, and that's virtually doing the same thing, provided it has to be in the form that we can integrate. We can't integrate x dm, that's not going to work, but we can write it in a form that we can integrate. So what we do is we write dm in terms of f of x, and if we can do that, then we're in a form where we can apply the process of integration. What we do is this then. We take our shape f of x and bounded by the x-axis, and we divide it into an infinite number of very, very thin rectangles. Very, very thin rectangles. We then work out the mass of all these individual thin rectangles. Then we work out the moment about the y-axis or the x-axis of all those very, very thin rectangles. Once we've got that function, we can integrate it and get the answer. This is what we do. Let me just concentrate on the coordinate for the x-coordinate of the centre of mass. And you can think about how we manage it for the y-coordinate. And you can use the previous example to help you. But look at the x-coordinate. Suppose we go along the x-coordinate, the x-axis, and we stop at some arbitrary point x, and we look at this rectangle here. Now, if we stop at x, and we take a tiny wee interval after x, and a tiny wee interval before x, and we evaluate f of x for the tiny, tiny wee margin of numbers, we should get the same answer for f of x, provided the interval is very, very small. The interval is very, very small, which we call dx, and we evaluate f of x at all of those points, we'll get the same f of x, which means the area of the rectangle will be dx times f of x. That's the area of it. Now to find the mass of that rectangle, which is multiplied by the area density, sigma. So dm will be sigma f of x dx. Now to find the moment of that rectangle, multiply it by the x-coordinate where you happen to be evaluating your tiny wee rectangle. If you want to find the coordinate for the y centre of mass, then you multiply the mass by half of f of x, as discussed in the previous example, and then we arrive at our two formulas as shown for the x coordinate of the centre of mass and the y coordinate of the centre of mass for our lamina. So let's use these formulas to find the centre of mass of my triangle in this orientation. Well, I can't just proceed willy-nilly. I've really got to look at this problem and think about it, and I can actually see the function I wish to evaluate in my formula is not one function that I called f of x. It has to be a difference of two functions. F of x is equal to 9 and g of x is equal to 3/2 of x. I like you to think about that yourself, but when I evaluate that function, I do indeed get the right answer, 2, 6. This is that was quite an important wee question, and I went into some technical details regarding the derivation of the continuous distribution of mass, but that's essential. That is very, very essential, because you will be asked to do things like this when it comes to other types of problems, where you've got this, where you're given the basic definition in integral form, and you have to write it in a form that you can integrate. That can be very challenging, but what we do, we build up. We do the easy ones first of all, we build up, and before we know where we are, we can then set up difficult integrals to integrate. So it's essential that I actually show you how to do that. Oh, and don't mention it.